Hey everyone, in this video, we're going to talk about upgrading the Ninebot Max G2 scooter. I'll show you how to swap out the stock battery for a bigger one, and that means way more range, like 2.5 times more. If your scooter now does around 30 kilometers on a full charge, with the new battery you'll get about 80 kilometers. And on top of that, I'll show you how to boost the power and speed from 25 kilometers per hour up to 35 or even 50 kilometers per hour. The whole idea is pretty simple. Inside the deck of the scooter, there's actually a lot of unused space. The original battery is kind of small, and there's just empty room on the sides. So I designed this custom battery that fits the shape of the deck almost perfectly and fills up all that space. That's how we get 2.5 times more capacity. And don't worry, no cutting, drilling, or soldering required. You just remove the stock battery and install the new one in its place. The whole upgrade takes less than 30 minutes and only needs a couple of hex keys and screwdrivers. And the best part? The scooter still looks totally stock. Nothing sticks out or grabs attention. I'll walk you through how to build this battery yourself. I'll share all the 3D models for printing and take you step by step through the whole process right here in my workshop so you can make one, enjoying the process and saving a bunch of money along the way. And at the end, we'll compare the final result with some other popular scooters, so you'll know exactly which option works best for you. Sounds good? Then grab a drink and let's go. I recently bought a Ninebot Max G2, and I'm really happy with it. It's a great scooter, powerful, reliable, with both front and rear suspension. The European version is limited to 25 kilometers per hour, but that's easy to hack by flashing a custom firmware. After that, it goes about 35 kilometers per hour. The only downside for me was the range. According to the specs, the scooter can do up to 70 kilometers on a single charge. But let's be honest, that's probably with a 40-kilogram Chinese girl riding on a perfectly smooth road. Meanwhile, I'm a big guy with a huge backpack, and I ride pretty aggressively. So in real life, I only get about 30 kilometers. I mean, 30 kilometers is probably fine for most people, but for me, it's a little tight. I live just outside the city, and my trip to the city center is around 15 kilometers one way. So 15 there, 15 back, that's already 30. Every time I barely make it home on the last drops of battery. Sometimes I even had to push the scooter after it died. That's when I realized it's time to upgrade the range. If you open up the deck of a Ninebot Max G2, you'll notice there's a lot of empty space inside. The stock battery is actually pretty small, so the internal space is used really inefficiently. I figured, why not build a custom battery that follows the shape of the deck and uses up all the available space? So what does it mean to build a battery? Well, most batteries are built pretty much the same way. Even though they look like solid rectangular blocks, inside they're made of standard cylindrical cells. For example, if you take apart the original battery, you'll find 60 of these 18650 cells. Look, I've taken 60 of the same cells and laid them out neatly inside the deck. There's actually room for more, don't you think? So basically, designing a new battery just means trying to fit in as many cells as possible. I decided to go with 21,700 cells. They're a bit longer, which lets us use the full depth of the deck. Let's see how many we can fit in. I managed to squeeze in 80 cells. Of course, we can't just put the cells inside and call it done. The next step is to design a proper battery case. Here's the model I came up with. This case holds all the cells, fits the BMS, and makes it easy to connect everything together. Then we do the following. First, I print the case. Then I fit the cells. Next, I weld the cells together. Then, install the BMS. And finally, wrap everything in heat shrink. Here it is, the new battery. As you can see, it perfectly follows the shape of the deck and fills up almost all the available space. That's what gave us a huge boost in capacity. Get this, the stock battery is 15,300 mAh, and the new one is 38,000. That's 2.5 times more. The new battery also has mounting holes, so it can be securely attached to the deck with 6 M4 bolts. And even though this new battery is a bit taller than the original, it still fits under the deck cover. So from the outside, the scooter looks completely stock. All right, the new battery's installed, the scooter is all put back together and fully charged. I went out early this morning and I'm planning to ride until the battery is empty. Here on the phone screen, you can see how far I've already gone, 13 kilometers. And just above that, the remaining battery charge, 83%. To make things easier to follow, I'll also show this info in the middle of the screen. So let's see how far we can go. The battery is finally almost empty, only 8% left, and the scooter has become really weak. It can't even climb a small hill anymore. So I'm finishing the test here. As you can see, I managed to ride 83 kilometers. That's a great result. You're probably wondering, 80 kilometers of range? That's a lot. My whole city is only 10 kilometers across. Who even needs that? Maybe it only makes sense for delivery workers or someone with really specific needs. Well, to answer that, imagine you're driving a regular car with a gas engine. Obviously, the power and speed don't depend on how much fuel is left in the tank. As long as there's gas, you can drive at full speed, and once it's empty, the car just stops. Electric vehicles are a bit different. When the battery is fully charged, you get full power and top speed. But once it drops to around 50%, you already feel a noticeable drop in performance. And when it gets down to 10 to 20%, the scooter becomes really slow and weak. So even though the total range is 80 kilometers, only the first 40 are going to feel smooth and enjoyable. In my experience, having 80 kilometers of range is just perfect. I can ride without stressing about battery level or looking for a place to charge. Also, things don't always go as planned. Some days get really busy and you need to ride a lot, back and forth. It's good to know the battery is ready for days like that. After installing the new battery, my scooter has a crazy range of 80 kilometers, but the top speed is still stuck at around 25 kilometers per hour. And hey, I promised 50 kilometers per hour at the start of the video. You don't think I was lying, right? Well, here's the thing. Speed and power don't just depend on the battery. They're also limited by the scooter's main controller firmware. This firmware puts restrictions in place to comply with local laws. For example, German versions are limited at 20 kilometers per hour, while US versions go up to 32 kilometers per hour. So just swapping the battery isn't enough to go faster. You have to flash the controller too. As of now, early 2025, here's how it works for Ninebot Max G2. You take out the controller, connect it to a programmer, plug that into your phone, and use a special app to flash a new firmware. I don't want to overload this video with a complete flashing tutorial, but I'll drop a link to another video with all the details. So check the description later if you need it. All right, I've flashed my scooter, and now it goes around 35 to 38 kilometers per hour. But that's still not the 50 I promised. So next, I'll show you how to push it even faster. The thing is, your top speed depends on the battery voltage. Basically, for every volt, you get about 1 kilometer per hour of speed. For example, a 36-volt battery gives you a top speed of about 36 kilometers per hour. So if you use a 48-volt battery, the top speed can go up to around 48 kilometers per hour. Remember earlier in the video when I showed you can fit 80 cells inside the deck? Well, you can group those cells in different ways. For example, 10 groups of 8 cells gives you a 36-volt battery, while 13 groups of 6 cells results in a 48-volt one. So now you can see why higher voltage matters. It directly increases your top speed. But a 48-volt battery also comes with two big downsides. First, you have to flash the controller to remove the built-in speed limits, otherwise the higher voltage won't make any difference. Second, the original built-in charger won't work with a new 48-volt battery. You'll need a new external charger, which means extra cost. And the last downside, you can no longer charge it directly from a wall socket like before. Let's install the 48-volt battery into the scooter and go for a ride to see what kind of top speed we get. As you can see, I was able to hit over 50 kilometers per hour. That's crazy fast. I want to make one thing very clear. Riding faster than 30 kilometers per hour is illegal, dangerous, and honestly just stupid. Electric scooters have small wheels, so even a random bump can make you fall, and the brakes are weak too, which means you might not be able to stop in time if a car gets in your way or a person suddenly steps out. So why upgrade to 50 kilometers per hour? Personally, I have two reasons. First, I live outside the city, and riding on empty country roads is much safer. Second, the scooter gets slower when the charge drops below 50%. But if your fully charged scooter is able to go 50 kilometers per hour, it can still hold a steady 30 even when the battery is almost empty. Now, about the range with the 48-volt battery, there's really no point in doing a full separate test. That's because the number of cells in the 48-volt and 36-volt versions is almost the same. 78 versus 80, which means the total energy is almost the same too. So if the 36-volt battery gives you 83 kilometers of range, the 48-volt battery will provide around 80 kilometers. By now, all these details and options might look a bit complicated, and you're probably wondering which upgrade is actually the best. Let me explain it, step by step. You start by buying a brand new scooter for around 600 euros. Out of the box, it gives you about 30 kilometers of range and 20 to 25 kilometers per hour of top speed. From there, you've got 4 upgrade options. The first and simplest option is to install a new big 36-volt battery without flashing any custom firmware. That gives you 2.5 times more range. The main advantage of this upgrade is that it's simple. You don't need to mess with firmware or buy an external charger. Just swap the battery. It takes around 30 minutes with a couple of hex keys and screwdrivers, and you're good to go. The only downside is that you won't get any increase in speed or power. But the upside is the scooter stays as legal as possible, which is a big advantage in countries with strict laws. This kind of upgrade will cost around 250 to 300 euros and add about 2.5 kilograms to the scooter's weight. The second option is the cheapest one. You keep the original battery, installing just a custom firmware. In this case, the range stays the same, but power and speed go up. You can reach around 35 kilometers per hour. The only downside is that flashing the firmware isn't very easy right now, since the scooter is still new and not well understood. But I'm sure simpler methods will be available soon. The firmware upgrade usually costs between 0 and 50 euros. I'll explain why a bit later. The third option is to install a new 36-volt battery and also flash a custom firmware. That gives you 2.5 times more range, more power, and a top speed of about 35 kilometers per hour. The only downside is that you'll need to figure out how to flash the controller, but in the end, you get a fast, powerful, long-range scooter that still looks completely stock. This upgrade will cost around 250 to 350 euros and add about 2.5 kilograms to the scooter's weight. And finally, the fourth option for the really crazy geeks. You install a new 48-volt battery and flash a custom firmware. You'll get 2.5 times more range, more power, and a top speed of about 50 kilometers per hour. Remember that you still need to flash the controller, and you'll also have to buy a new 48-volt charger. But in the end, you get a super powerful and fast scooter. This upgrade will cost around 300 to 400 euros. It adds about 2 kilograms of weight, which is half a kilo less than the 36-volt version, because you can remove the built-in charger, which you won't need anymore. A lot of you are probably thinking, is it even worth upgrading a small scooter like this? Especially when the upgrade costs almost half the price of the scooter itself. Wouldn't it make more sense to just buy something bigger and more powerful from the start? Well, in my opinion, there are two really good reasons to upgrade a small scooter instead of buying a big one. First, and this matters if you live in a country with strict laws, in some places, even small scooters need to be registered. And if you go for a bigger model, you might even need a driver's license. You won't be allowed to ride on bike lanes or sidewalks, and overall, you'll be treated more like a motorcycle than a scooter. So yes, you can buy a big, powerful scooter, but what's the point if you end up stuck in car traffic? Meanwhile, with a small scooter, you can legally ride on bike lanes, sidewalks, and even on the road sometimes. Small scooters, like Ninebot G2, don't draw much attention. They're just a normal part of city life. Even the police usually don't care. Second reason, parts and service. Popular small scooters are well known. Most of their common issues have already been solved, and spare parts are easy to find. So if something breaks, you can take your scooter to almost any repair shop, or even fix it yourself after watching a couple of YouTube videos. Bigger scooters are a different story. They're not very common, there's not much information about them, parts are hard to find, and most repair shops don't really know how to fix them. So if you buy one, you might end up with a lot of trouble. So, if you've decided to upgrade your scooter, there are two ways you can go. If you are looking to buy a ready-to-use battery, check out my online store. We are based in Poland and ship to all European Union countries except Cyprus and Malta. But if you prefer making your own battery, no problem. I've prepared a step-by-step tutorial where I show exactly how I design and build it in my workshop. Now we're getting to the real DIY action. And hey, before we dive in, give this video a like and subscribe to the channel. That really helps me out. More people will see the video, I'll get more customers, make some money, and keep creating unique, high-quality content for you. Let's start by taking a closer look at the scooter's deck and checking how much space we actually have to work with. Here's what I measured. Width, 125 millimeters. Length, 360 millimeters. As you can see, the front part of the deck narrows and curves. That's something we need to keep in mind. Width at the narrow part, 85 millimeters. Distance from the front to the start of the curve, 70 millimeters. Mounting tab spacing, 127 millimeters horizontally, 108 millimeters vertically. Inner hole diameter, 4 millimeters. Outer diameter, 7 millimeters. Now let's estimate how many cells we can fit into the available space. I've marked the maximum dimensions of the battery with a dashed line. First, I tried the simplest rectangular layout, 5 cells across and 16 along the length, for a total of 80 cells. At first glance, it seems fine, but if you look closely at the left side, where the deck curves, you'll see that the cells go over the limit. Also, some cells are blocking the mounting tabs, so we'd have to trim the mounts to make it fit. Another problem with this layout, there's no space left for the protection electronics, while there's a lot of unused space on the sides. To fix all that, we need a more advanced honeycomb layout. Here we're using the full width, and at first glance it fits up to 88 cells. But we have to leave room for the mounting tabs, so 3 cells are out. And on the right side, we need space for the BMS, so we remove 1 more row. That leaves us with exactly 80 cells, which is just what we need. We can build either a 36-volt battery in a 10 series 8 parallel configuration, or a 48-volt battery in 13 series 6 parallel. Let me show you a basic 3D model to visualize it better. So here's what the 80 cells look like. And here's the case, with holes for the mounting tabs and space at the front for the BMS. Again, this is just a first draft of the battery design. There's still a lot of work to be done, but I'm skipping that in this video because this is a practical battery building guide, not a 3D modeling tutorial. So here's the finished case. On top, you'll see a bunch of cutouts for wire routing and cell connections. At the end of the case, there's space for the BMS. On the bottom, you'll also see a bunch of cutouts for wire routing and cell connections. And as you can see, the battery is a bit rounded. That's because the deck also curves in that area. One more detail, the battery also has an angled edge. That's because there's a weld line inside the deck, right where the battery ends. So I had to get creative and fit around that. The final length of the battery is 343 millimeters, which is quite a lot when it comes to 3D printing. The thing is, most budget printers have a bed of around 250 by 250 millimeters, so the case we designed just won't fit. I also have a 300 by 300 printer, but that's not enough either, even if I place the battery diagonally. So you need something bigger, at least 350 by 350. For example, Creality CR10 Max or the Ender 5 Plus would be fine. Alright, let's drop the model into the slicer and see what we get. It showed around 40 hours of print time and about 500 grams of filament usage. Sounds good. Let's start the print. And here we are. Almost 2 days later, the case is done. Of course, 3D printing isn't perfect, so the case still needs a bit of cleanup, removing supports and doing some post-processing. And this is what we ended up with. Looks pretty good. Now it's ready for the next step, installation of the cells. We're now making a 36-volt battery in a 10 series 8 parallel configuration, which means we need 80 cells. So the first step is getting the cells. Personally, I've been ordering from a Dutch store Encon for years, and I'm super happy with them. Prices are fair, delivery across Europe takes just a few days, and most importantly, they only sell genuine cells with a 100% quality guarantee. On the flip side, I really don't recommend buying from places like AliExpress. There's a high chance you'll get scammed. They might send lower-grade cells than advertised. This is not the place to save money. The overall quality of your battery will directly depend on the quality of your cells. So my advice, it's better to pay a bit more, but buy from a trusted source. Here I've sorted the available cells by capacity. As you can see, the highest capacity ones are the Samsung 58E with a capacity of 5,300 milliamp hours and a price of €4.50 each. But here's the thing, the highest capacity cells are often overpriced. You can go with something just 10% lower in capacity, but nearly half the price. My personal favorite is the Samsung 48G with a capacity of 4,800 milliamp hours and a price of around €3 each. That's what I usually use when building my batteries. So I ordered 80 of them, and 5 days later, here they are. The first thing to do is stick paper insulator rings on the positive terminal of each cell. That adds a bit of extra safety when we'll be spot welding the cells together using nickel strips. Next, it's a good idea to measure the voltage of each cell and make sure they're roughly the same, within a few hundredths of a volt. That's how you check if there's a bad cell with unusually low voltage. All right, rings are on and voltages are looking good. It's time to start placing the cells into the case. With all the cells in place, it's time to start connecting them. The standard method is using metal strips and a spot welder. Spot welding itself is a whole topic, full of little tricks, tools, and details. I'm not going to turn you into a welding guru here, but I will show you the basics. Let's start with the strips. Most builds use nickel strip that's 8 millimeters wide and 0.15 millimeters thick. It gets cut into different lengths, depending on how many cells it needs to connect. Here's the welding layout. One for the top, one for the bottom. We'll need 4 different strip lengths for 2, 3, 4, and 5 cell connections. Here's a little trick to speed things up. I stick a piece of paper on the desk and mark the lengths. 2 cell, 29 millimeters, 3 cell, 51 millimeters, 4 cell, 73 millimeters, and 5 cell, 95 millimeters. Then I cut the strips with scissors. And while I'm doing that, here's something useful to know. Nickel strip comes in 2 types, pure nickel and nickel-plated steel. Pure nickel conducts better and doesn't rust, but it's more expensive, harder to find, and a bit trickier to weld. Nickel-plated steel is the opposite. It's cheap, easy to find, and simple to weld, but it doesn't conduct as well, and it will rust if water gets in. Personally, I prefer nickel-plated steel. It welds reliably, and honestly, it's just nice to work with. As for rust, not really an issue. If the battery's built and installed properly, water's never getting in. And what about conductivity? True, it's not as good. That's why I use a smart layout that spreads the current evenly. And in high-load areas, I weld multiple layers of strip. Okay, strips are all set. I've got 26 strips for 2-cell connections, 40 strips for 3-cell, 14 strips for 4-cell, and 1 5-cell strip. It's time to weld. We're starting with the bottom side of the battery, and right away we run into a problem. If you press on a cell, it sinks into the case, and that makes welding tricky. To fix that, I printed a stand with little columns that supports the cells, keeping them from sinking. And now the pack stays solid and doesn't move. That makes welding much easier. So I take the strips and weld them with a spot welder. Now you might be wondering, how do I know which strip goes where? And where should I weld single or double layers? Take a look. I have created a full layout that shows the correct order and placement for each strip. Looks messy at first, but I will walk you through it. We start with line A1. That's a strip over 2 cells marked A1. Then A2, which connects 3 cells. Make sure to weld all the cells the strip touches, not just the ones on the ends. Then A3, A4, all the way up to A9. Then we move to B1, B2, and so on. It's really important to follow the layout because it balances the current across the cells. If you just randomly weld strips, the current will be uneven, which causes worse performance and faster cell degradation. If you're building just one battery, honestly, try finding a local shop that can weld it for you. It will probably be cheaper and faster than buying your own spot welder. And if you're really serious about it and want to buy your own spot welder, I'd recommend checking out some in-depth videos. They cover welding techniques and how to choose the right equipment. In my case, I started with a Chinese Sunko 737G, and now I use a German-made K-Weld. Super reliable and really nice to work with. All right, one side is done. Let's move on to the other. Here's the top side welding layout. It's useful both for DIY welding and for giving the layout to a shop. And here's what the battery looks like after welding is done. The battery is almost finished, and now it's time to install protection electronics, the BMS. But why does it need electronics? I mean, it's a battery, not a calculator, right? Let me explain. Take a look. I've built this tiny, lightweight battery. Meanwhile, this little toy provides up to 10 kilometers of range. That's because lithium cells have a really high energy density. They pack a lot of energy into a small space. But they also have some downsides. The biggest issue with lithium batteries is fire risk during charging. If you overcharge a lithium cell, it can literally catch fire, and we're talking serious damage. That's why the BMS keeps track of the charge level and stops charging when needed. The second issue is that lithium cells should never be fully discharged. If that happens, they get permanently damaged, from a small drop in capacity to a completely dead battery. That's why the BMS watches the charge level and shuts down the battery before it gets too low. For example, when your scooter shows 0% and won't move, there's still some energy left inside. The BMS just blocks it to prevent deep discharge. The third problem, lithium cells don't like extreme temperatures. If the battery is frozen to 0 degrees, you need to warm it up before charging. And if it gets overheated to 50, you also need to let it cool before using. Ignoring this can damage the battery. That's why the BMS keeps an eye on the temperature and stops charging or discharging when needed. The fourth issue is cell imbalance. That can happen because the battery is made of a few cell groups connected in series. In a perfect world, all the groups would have the same voltage, like 3.6 volts each, adding up to 36 volts. But in real life, some cells might drop in voltage, while others go too high. Look at these two cells at the top. Let's say one drops to 3.2 volts and the other rises to 4 volts. It's a tricky situation because the total voltage is still 36 volts. So if you just measure the battery output, everything might look fine. But the battery is already in trouble, you just don't see it yet. This is called imbalance. If you're lucky, it just reduces capacity. But in worst cases, it means something's really wrong, like a broken weld or a failing cell. To deal with that, the BMS connects to each cell group individually. That way it can track all 10 voltages. And if the BMS detects an imbalance, it can adjust the voltages. This process is called balancing. So now you know why lithium batteries need protection electronics inside and what problems it solves. But we're not building just a random battery. We're building one for a Ninebot scooter. And that makes it a bit more complicated. As I mentioned before, most batteries are basically a black box, which means the BMS takes care of the cells, while you just get the charge and discharge plugs. You don't really see what's going on inside. That's how most cheap batteries work. But if you look at the original Ninebot battery, you'll see it has 3 plugs. 2 of them are for charge and discharge, standard stuff. And the third plug is special. It's a digital data line. Remember how I said the battery is like a black box? Well, this data line lets you see what's going on inside. If you connect the scooter to a smartphone app, you'll see all kinds of useful info. Cell voltages, temperature, charge and discharge current, battery serial number, and more. All of that comes through the data line, which connects the battery to the scooter's main controller. It's a super useful feature, but there's a little problem. If you try to use a cheap battery without that data line, the scooter just won't accept it. That's a real issue for anyone trying to install a custom battery. Luckily, there are 2 ways to solve this problem. Option 1. Flash the scooter's controller with a custom firmware that disables battery communication. This way, the scooter stops checking for the data line, and you can use any regular battery. The downsides: you won't be able to see battery info in the app anymore. And flashing firmware can be tricky sometimes. Option 2. Use a smart BMS with a proper data line, just like the original battery. This way, you don't need to flash any firmware, and you still get full access to battery info through the smartphone app. The downside is price. The smart BMS costs around €70, while a regular cheap BMS is just about 20. For this project, I will be using the Smart BMS to keep things simple, so you can just swap the old battery for the new one, and that's it. No need to mess with firmware. Let's start by placing the BMS into the battery. I'm using 2 strips of double-sided foam tape to hold it in place. Now let's get to the wiring. The BMS comes with a whole bunch of wires sticking out, but it's not as complicated as it looks. This is the main battery output. It goes to the scooter's controller and supplies power. This one is the charging input. It goes to the charger. And here's the data line for communication between the battery and the controller. So these 3 wires will stick out of the battery, while the others need to be wired inside. To figure out the wiring, let's use the BMS user manual. The first thing you'll notice is a warning. You have to connect the wires in the right order, otherwise you could damage the BMS. So we start with wire number 1. It's a black power cable that connects to the battery's negative lead. We run it to the back. And solder it across these 8 cells. First, we tin the nickel strip. Then we strip the cable. Then we solder the cable lightly just to hold it in place. Then we go back and properly solder every contact. You can see I'm pressing the wire down with tweezers. That keeps the joints nice and flat, which becomes important later when you try to close the case. Okay, the first wire is done. Next is wire number 2, the red power cable that connects to the battery positive. This one is much easier since the positive terminal is right next to the BMS. So we tin the strip. Strip the wire and solder it. Now this little guy here is a temperature sensor. It goes into a special slot right next to one of the cells. For better thermal contact, I add some thermal paste. And the last to connect is a flat ribbon cable with 16 wires. Why so many? Well, this BMS is compatible with a wide range of setups, up to 54 volts, and that requires 16 balance wires. Meanwhile, we're building a simple 36-volt battery, so we only need 11 balance wires. But how do you get 11 from 16? Easy, just join some of the wires together. Like this, 2 wires become 1, then 3 more become 1, and another 3, same thing. I'm going to split the ribbon now, just to avoid mistakes while connecting later. Here we go, 11 balance lines from B0 to B10. Now it's time to start wiring. Take a look at the diagram. See those green circles with numbers? That's where the balance lines get soldered to the pack. Before running the wires, I prepare the nickel strip, just tinning the connection points with a soldering iron. Then I lay down strips of double-sided tape to hold the wires in place. And now we're ready to route the wires. I start with the first wire, peel it off the ribbon, lay it down on the tape. Cut to length, strip and tin the end, and solder. Next, the second wire. Run it through a special hole to the other side of the pack. Then lay it down to the desired soldering point. Strip, tin, and solder. Back to the top side and connect the third wire the same way. Now here's something new. Take 2 wires from the ribbon, but treat them as a single line. Route them together. Strip and twist the ends. Tin and solder. Then we keep routing the rest. When you get to the triple wire, nothing tricky here. Just grab 3 wires, route them, twist the ends, and solder them together. Keep going like that until all 11 balance lines are connected. And that's it. The BMS is installed. Before we close the battery case permanently, let's check if it even works. If you measure the output voltage with a multimeter, you'll probably see 0. Don't worry, that's expected. By default, the battery stays off after it's built. To activate it, we need to plug in a charger. Let's use the scooter's built-in charger for this. Carefully place the battery inside the deck, better on its side since the top and bottom are still open and easy to short. If something metal gets inside, like a loose screw, it could cause a short circuit, and that can lead to serious damage. Find the charging connector and plug in the new battery. Then connect the scooter to the wall. If everything's working right, the battery will turn on and you'll see about 36 volts at the output. We paid extra for the BMS with a data line, so let's use it. I will connect the battery to a computer to check that everything's fine and adjust a few settings if needed. Take a look. This little adapter comes with the BMS, so I'm plugging the battery in here. Then I connect the adapter to my computer using a USB cable. Next, we have to open a browser and go to embedden.com/bms-utility. On that page, click Connect. Select the COM port and hit Connect again. Let's start with the battery monitoring section. It shows useful data like output voltage, current draw, remaining charge, cell temperature, BMS temperature, and individual voltages for all 10 cell groups. Everything looks good here. Seems like the battery is in good shape. Now for the settings. The most important thing is to set the correct battery capacity. We're using 4,800 mAh cells, 8 in parallel. That gives a total of 38,400 mAh. Let's round that down and set 38,000. You can also set optional fields like the battery's serial number and production date. They don't affect how it works, but they are displayed in apps, which looks quite professional, especially if you're building a battery for sale. The other settings are already fine for a Ninebot Max G2, but if you want to go deeper and fine-tune all the parameters, check out the BMS user manual. It explains every setting in detail. So, the battery is tested and set up. Now it's time to close the case and finish the build. First, let's install this little front panel to cover up the wires. I'm using 2.5 millimeter countersunk screws for that. Next, we need to close up the top and bottom of the battery. For this, I picked fiberglass laminate, a very durable and heat-resistant material, which is still easy to cut and shape. I'm using a 0.5 millimeter thick sheet, and that part is critical because the battery has a height limit, so even a millimeter makes a difference. If you go thicker, the new battery just won't fit inside the scooter. Lay the battery on the sheet, draw outlines around it with some extra margin. And then cut the panels. To attach the covers, I'm using double-sided tape, preferably the industrial kind, reinforced with fiberglass. Meanwhile, regular office tape is only good for sticking notes to your fridge. Start by sticking the tape strips onto the bottom side of the battery. Trim the ends of the tape and peel off the yellow backing. Now carefully place the cover. Since we left some extra margin, we don't need to get it perfectly aligned. Anything over the edge can be trimmed with scissors. Next, we need to drill the mounting holes. I'm using a 5mm drill bit and starting the hole from the other side. The battery case works as a guide, so the holes come out clean and exactly where they should be. Okay, one side finished. Moving to the top, same steps again. Tape, cover, trim, and drill 5mm holes. But there's one difference. On this side, we need to widen the holes to 8mm. I'm using a step drill for that. And finally, the holes are ready. Now use a file for trimming the covers so nothing goes beyond the edge. Round off any sharp corners because we don't want them cutting the heat shrink later. And finish it off with some sandpaper. Next, it's time to wrap the battery in heat shrink. You'll need 200mm wide tubing. Cut off a piece with some extra length on both ends and slide it over the battery. Use a heat gun set to around 200 degrees. Start by shrinking the edges. The key here is even heating from all sides. That way it shrinks nicely with no folds. Quick tip: try moving your lamp to get better light. Find an angle where you can clearly see all the folds and bumps. That helps you to heat only where needed. It's not difficult, but it does take some practice. Don't stress if it's not perfect the first time. Just get at least 2 meters of shrink, so you've got a few tries if something goes wrong. Now we need to reopen the mounting holes that got covered by the shrink. They're easy to spot, so just carefully drill them out again. If the bit is sharp, it's easy. The shrink behaves more like plastic than soft film. And finally, the holes are ready. Next step, trim the extra shrink at the front and back using a sharp knife. Now it's time to seal the ends. I'm using self-adhesive vinyl, the same stuff used for car wraps. The color is blue, same as the heat shrink. Draw the outline. and cut a slightly smaller piece. Then just stick it on. Repeat the same for the other end. It's a bit trickier because you have to work around the wires. And the final step. To protect the wires from bending and seal the battery against moisture, apply some silicone to the wire exit point. Once applied, let it cure overnight. And that's it. The battery is done. As a finishing touch, I'm adding a sticker with the specs. And there's really something to be proud of. 38 amp hours of capacity, Samsung cells, in a clean professional build. All right, we just built a 36-volt battery. But what about 48 volts? The one that lets you hit 50 kilometers per hour? Well, here it is. Can you see any difference except the label? Probably not, because the two batteries look almost the same. That's why I'm not going to waste your time showing the full process again. Instead, I'll just highlight the three real differences. First, cell layout. The 36-volt pack has 10 groups of 8 cells, while the 48-volt one has 13 groups of 6 cells. So the cases are also a bit different around the nickel strip layout. Here's the welding diagram for the 48-volt pack. And this is how it looks after welding. Second difference, power wire routing. On the 48-volt battery, the positive terminal is on the bottom, so the red power wire goes through a special hole to the other side of the pack. And gets soldered there. Third difference, balance wire setup. The 36-volt battery has 11 balance lines, while the 48-volt one has 14. Still the same 16 wires in the ribbon, but now we group them differently to get 14 lines instead of 11. No wonder the solder points on the pack are different too. The rest stays the same. Stick the fiberglass panels, wrap in heat shrink, drill mounting holes, seal the ends, silicone the wire exit point, and that's it. The 48-volt battery is finally done. So you've got your new extended battery. Maybe you built it yourself, or maybe you bought a ready-made one. Either way, now it's time to install it into the scooter. Let's do that. First, we need to remove the bottom cover. Use a T20 Torx bit, ideally with a power screwdriver. Unscrew all 16 bolts and take the cover off. Now take a look inside. The deck is split into two parts, front for the battery and back for the controller and charger. The wires run through a hole in the divider, sealed with black silicone. Since I'm disconnecting the battery, I need to remove the seal. A flat screwdriver works well, just be careful with the wires. When the wires are free, go ahead and unplug all 3 battery connectors: the charging plug, the data line, and the main power connector. Then pull the wires to the battery side. Now remove the screws that fix the battery in place. You'll need a 3mm hex key for that. Okay, the old pack is out, halfway done. Time to install the new battery. Start by placing it inside the deck. Line up the mounting tabs on the deck with the wide holes on the battery case. Then screw it down using 6M4 by 75 bolts. And don't forget to use washers, at least 10mm wide, to spread the tension across the plastic. It's really important to use thread locker here. If you skip it, vibrations may loosen the bolts, causing the battery to rattle and get damaged. No thread locker? Just borrow some nail polish from your girlfriend. And if you're getting the battery from my store, no worries, everything's already in the box. All right, the battery is secured. Let's plug everything in. Run the wires into the rear section of the deck. Start by connecting the power plug. This one is a bit tricky since the socket is deep and space is tight. And nothing to worry about if you hear a crack or see a spark. That's normal. It's just the controller's big capacitors charging up. Next, connect the data cable. And finally, the charging plug. That's it. The new battery is installed. Let's turn the scooter on and see if it recognizes the new battery properly. I open the M365 Tools app, connect to the scooter, and switch to the battery tab. You can see the same values we said earlier: serial number, capacity, and the manufacture date. Looks like everything's working, so we can close up the deck. And again, I really recommend using thread locker here. Without it, the screws can loosen from road vibration, and you might come home missing half of them. So yeah, like I said at the start, swapping the battery is super easy, and from the outside, the scooter still looks completely stock. As a final step, I check the scooter weight, just to see how much the new battery adds. It came out to 26.7 kilos, while the stock one, 24.3, so we're up by 2.4 kilograms, which is around 10%. Not bad considering we more than doubled the range. The upgrade looks really cool, but what about the price? Let's go through it step by step, starting with the battery. There are just two options. Option 1, build it yourself. The biggest cost here is the cells. You'll need 80 of them, about €3 each. That's 240 euros in total. Then you need a smart BMS, another 70 euros. As for the battery case, you can print it yourself. Filament and electricity will cost around 10 euros. Or if you order a print, expect to pay about 3 times more, 30 euros. Other stuff like nickel strip, fiberglass sheet, shrink wrap, silicone, 20 euros more. So in total, a DIY battery will cost you around 350 euros and some serious work. Option 2, just buy a ready-made battery. For example, I sell it for 390 euros in my store. And there is a little bonus. After installing the new battery, you can sell the stock one. It goes for around 100 euros, which means the final upgrade cost drops to 290 euros if you buy a ready-made battery, and $250 if you build it yourself. Now let's talk about flashing the controller. And again, you have two options here. First option is Xiaodash. That's what I'm using on my scooter, mostly because of the great support they provide. I just joined their Telegram group, asked a bunch of newbie questions, and got clear answers right away. But this convenience isn't free. The price of this firmware starts at €30. Second option, scooter hacking. They don't charge money up front. Instead, they ask you to donate if you want. So if you're a student, you can just flash your scooter for free, no problem. But if you're a grown man with a decent job, I think it would be fair to donate for supporting the guys. By the way, flashing the firmware can be tricky, especially on newer models. You can bring the scooter to a repair shop, but it won't be free, of course. So the bottom line, the firmware upgrade can cost you nothing if you do it yourself with scooter hacking and skip the donation. Or about €50 if you buy Xiaodash and pay for flashing at a shop. You can find all the links, Telegram groups, websites, in the description below. One last thing, remember you need a new external charger for a 48-volt battery? You can get one from AliExpress. I recommend the YZ Power brand. Good quality, tested many times. To charge overnight, go with a 3 to 4 amp model. You can see here, the price is around €40. Double check the output plug. You need RCA plug X for this scooter. And pick the wall plug, depending on your country. By the way, if you are based in the European Union, you can get the charger from my store. It costs a bit more, but comes with warranty and fast delivery from Poland. Check the description for links to both options. Now, everything's clear about the build and the budget, so let's review all the upgrade options again and pick the best one. You start by buying a brand new scooter for around €600. Out of the box, it gives you about 30 kilometers of range and 20 to 25 kilometers per hour of top speed. From there, you've got 4 upgrade options. The first and simplest option is to install a new big 36-volt battery without flashing any custom firmware. That gives you 2.5 times more range. The main advantage of this upgrade is that it's simple. You don't need to mess with firmware or buy an external charger. Just swap the battery. It takes around 30 minutes with a couple of hex keys and screwdrivers, and you're good to go. The only downside is that you won't get any increase in speed or power. But the upside is the scooter stays as legal as possible, which is a big advantage in countries with strict laws. This kind of upgrade will cost around €250 to €300 and add about 2.5 kilograms to the scooter's weight. The second option is the cheapest one. You keep the original battery, installing just a custom firmware. In this case, the range stays the same, but power and speed go up. You can reach around 35 kilometers per hour. The only downside is that flashing the firmware isn't very easy right now, since the scooter is still new and not well understood. But I'm sure simpler methods will be available soon. The firmware upgrade usually costs between €0 and €50. The third option is to install a new 36-volt battery and also flash a custom firmware. That gives you 2.5 times more range, more power, and a top speed of about 35 kilometers per hour. The only downside is that you'll need to figure out how to flash the controller, but in the end, you get a fast, powerful, long-range scooter that still looks completely stock. This upgrade will cost around €250 to €350 and add about 2.5 kilograms to the scooter's weight. And finally, the fourth option for the really crazy geeks. You install a new 48-volt battery and flash a custom firmware. You'll get 2.5 times more range, more power, and a top speed of about 50 kilometers per hour. Remember that you still need to flash the controller, and you'll also have to buy a new 48-volt charger. But in the end, you get a super powerful and fast scooter. This upgrade will cost around €300 to €400. It adds about 2 kilograms of weight, which is half a kilo less than the 36-volt version, because you can remove the built-in charger, which you won't need anymore. In the end, for 900 euros, you get a scooter with a realistic range of about 80 kilometers and a top speed between 35 and 50 kilometers per hour. The only downside? It's heavy, 26 kilos. That's the price you pay for serious power, solid frame, and full suspension. It's great while riding, but carrying all that metal upstairs isn't much fun. So if you want something lighter and simpler, take a look at Xiaomi electric scooters. For example, Xiaomi Pro 2. The scooter itself costs around 500 euros, and another 300 for an extended battery, so 800 in total. You get about 50 kilometers of range, a top speed between 35 and 50 kilometers per hour, and just 16 kilograms of weight. That's 10 kilograms lighter than the Ninebot G2. Looking for something even lighter and cheaper? Then take a look at Xiaomi M365, 1S, or Mi 3. The scooter itself costs around 400 euros and another 300 for an extended battery, so 700 in total. You get about 40 kilometers of range, a top speed between 30 and 45 kilometers per hour, and just 14 kilograms of weight. In general, Xiaomi scooters are high quality and super popular. They're perfect for city riding on good roads, especially if you weigh under 70 kilos. A full guide for upgrading these scooters is upcoming. I'm currently working on it. Subscribe to the channel so you don't miss the new video. And while it's still cooking, check out my blog. There's already a detailed tutorial on building an extended battery for Xiaomi scooters. Or, if you prefer something ready to install, visit my online store. You'll find a lot of cool stuff for Xiaomi and Ninebot electric scooters. So I have explained everything, showed everything, and yes, promoted everything too. But let me also advertise my public Telegram group, a place where you can ask questions about scooter upgrades and repairs, or just talk with the community. And that's it for today. See you in the next video.